Test. Okay. So hello everybody, it's good to see you all again. I'm glad that we made it to week 4. I know that most of you have been working very diligently on your first lab, and I think I welcome any questions. If there's any major concerns you guys have about it, because again it's going to be due this evening, please or tomorrow evening, sorry. Please come discuss with me. I saw that there's some questions that were posted to Canvas, so I'll try to get to those after the class and make sure that everyone's caught up to speed. Hopefully, if you guys have questions there, you can also answer each other's questions and help out a little bit with each other there. Today, what we're going to be covering is a space of different topics, and that all somewhat relate. We'll be beginning with this concept of the Ethereum name service, which builds a little bit on our understanding of ERC standards from last week. And within the parameters of discussing security this week, we'll discuss a little bit about this concept of wallets, crypto wallets, and also we'll be balancing some of this discussion with more app development focus by looking at smart contract design patterns. Yes? Oh, thank you. So I guess the projector will start up in a second. So, yes, just our introduction. We have our understanding of what we're going to be discussing today: the Ethereum name service, wallets, and smart contract design patterns. And so, just to make a quick comment on how this all connects. So, wallets again are something that are going to be helpful for you to understand how to securely access your funds and send them, and kind of understand how the user interface for some of this access to Web3 and the blockchain ecosystem is done. And moving into smart contract design patterns, we'll be discussing again how to design your contracts more efficiently and securely. So the intended learning outcomes of today's lecture, we'll be looking at how ENS works, including its decentralized nature, this idea of the smart contract registry, the process of forward and reverse lookups. In terms of crypto wallets, we'll be differentiating amongst different kinds of crypto wallets, comparing and contrasting hot and cold storage wallets, including their security, usability, and other use cases. And finally, for smart contract design patterns, we'll be understanding how these different design patterns make smart contracts more secure, provide additional functionality while designing decentralized applications, and also help with things like auditing as well. So just to dive in with ENS, these are the kind of high-level things that we can discuss with the ENS. The ENS is a decentralized naming service similar to DNS. It's a registry for smart it's instantiated as a smart contract. There are these forward and reverse lookups standards set in ERC 137 and 181. Is referenced, all of the different websites or applications are referenced using the hash tree, and the registry uses the resolver contract to provide this kind of information. So this is just a high-level speed through, but we'll just dive into each of these points in a little bit more detail here. So the decentralized naming service is something that maps human-readable domain names to Ethereum addresses and other metadata. So this is similar to when you go onto google.com or lego.com or what have you. There is an actual IP address that this website is actually hosted at, but by having some human-readable web addresses, you're able to type in or tell somebody what your website name is, and they can remember it easily and type it in. And then by having a domain name service, a DNS, this is how the internet typically allows you to access different websites that are hosted online. So by having a decentralized version of this, you're able to host your web applications in terms of decentralized smart contracts, and also still tell people, actually, this particular website, you can just go to, coin-io, and it's going to be hosted in a decentralized manner. So this decentralized naming service is, again, something that maps these human-readable addresses to domain names, as well as other metadata. And again, this provides a more user-friendly way and easy to remember domain name registry. So again, this is instantiated like all other programs that are built onto Ethereum as a smart contract. And so again, when we think of smart contracts, we have this idea that we can have money, built into the ecosystem. But again, any kind of program, any kind of decentralized web application is going to be instantiated in a program that consists of smart contracts itself. And again, smart contracts are the individual files that make up together a particular program or decentralized application. And this contract stores information about the domain names and their associated addresses, as well as other metadata such as IPFS hashes. So can anybody remember our first kind of opportunity for X credit? Can anybody remember, or for participation credit, can anybody remember what do we talk about in the past about IPFS? Why is this important? Why is this something that we care about in the context of web applications in Web3? So just to refresh your memory a little bit, we talked about it in the context of NFTs and, for example, digital artwork. But what was IPFS, and why was this important for us to pay attention to? Okay, so yes, and so it's IPFS is it stands for Interplanetary File System. It's where you upload the data, and you want to expand why is this important, for example, in the context of NFTs?
I think it's a single point of reference for like all the data across the data.
Okay. Not quite, but I can get your name just to say, Brian. Oh, yeah. Okay. Other guesses? Why was IPFS important, for example, in the context of NFTs? It does store data. Yes. Okay. To give a hint, I'll say if you're storing, remember if we're talking about storing large files or large pieces of information on the Ethereum blockchain itself, it can be quite expensive. So in that context, like, is there a good reason why we would want to store any kind of information in IPFS? So so for those of you who are remembering our discussion from last time, if you have NFT artwork, although the file that the NFT artwork links is referencing, it might just be an image, might just be a JPEG. Even storing a JPEG on chain, on the Ethereum blockchain, is incredibly expensive. And so what you would have instead is within the smart contract of the system that you have built, you might have some metadata, such as, if we talked about the Bored Ape example, what kind of color the ape is and what kind of hat it has. But if you actually wanted a picture of the ape with some pixels, again, would be very expensive to store in Ethereum itself. And so IPFS is a decentralized data storage system, and it allows us, for example, to store pictures such as these Bored Ape pictures in a safe place that's the server is not going to change in the back end. So any kind of data that's going to be more than some trivial amount of metadata or some small amount of information would generally be offloaded from the main Ethereum blockchain into IPFS. And so is there any questions about this? So this is just something to remember. IPFS is going to be one of our main kind of decentralized data storage areas. So typically you might have SQL or you might have other kinds of files that your web applications are pointing to. And if you're going to have any of that kind of data, store it off chain. And some other, if you wanted it to be decentralized, IPFS is one good way to do this. And so ENS, the Ethereum name service, not only is pointing to particular smart contracts, but also if you're trying to point to particular pieces of data that's out there in IPFS, this is also a registry that will keep track of that kind of information. It does this in a fairly simple manner. It's going to be allow you to use these standards or these fixed functions that allow you to both do forward lookup and reverse lookup. So we'll talk about that in a second in more detail here. In a couple slides. But in general, how this works is that we use a hash tree to reference domain names and their associated information. And so if you put in a domain name, it quickly just has a hash tree that to store this information and just quickly gets this and makes sure that the information, again, is kind of tamper-proof and immutable. How this ends up working is that you have a registry to find a resolver contract, and this provides information on the address and a supported interface as well. So the ENS owner is allowed to change and resolve linkages as well. And they can also update Ethereum addresses associated with domain names or modify the resolver contract associated with the domain name. So what this is saying here is that if you have a particular website and or at least a domain, and you want to change the backend, you can, if you're the owner of this particular resolver contract, then you can change the linkages to this from the front end to the back end if you're registered as the person who's in charge of this particular domain name. So again, the resolver owner is allowed to change the address linkage and yes, update the Ethereum addresses associated with the resolver contract and modify any of the supporting interfaces associated with that address. So what this looks like in general is we have this ENS registry that has Ethereum files or whatever kind of files you want. And this resolver method is set by the ENS owner using a set resolver method. And this this resolver object has addresses associated with it, and also it has a understanding of what kind of interfaces are going to be able to interact with the web application you're building. So is it mobile only? Is it desktop only? These are kind of things that you can modify within this resolver contract. And again, this is controlled by the person who set up the website themselves. So this all is just a little bit of a technical background to understand, again, how this overall web application system works when we're talking about decentralized applications. This is something that if you start building your own applications, this might be something that you start to dig into as you start launching them and trying to put them to become public-facing websites. So now we're going to pivot away from this. If there's any questions about the ENS, again, it's a very high-level concept. I just thought I'd introduce it for now, so we kind of understand how the ecosystem works at a technical level a little bit more. But if there's any questions, I'll be happy to address them before moving on. Yes.
What's the point of the resolver contract?
So the resolver contract, again, is we want to separate the fact that there's a overall, there's one contract that's managing all of the different, it's kind of a compository or an amalgamation of all of the linkages between domain names and the equivalent of IP addresses, right, of smart contracts. And so if you want to yourself put a web application up there, you're not going to be editing the resolver contract yourself. That's going to be owned by somebody else. So you're not going to be editing the ENS registry yourself. That's owned by essentially the people who are managing the Ethereum Foundation. What you can edit, on the contrary, is a resolver contract, and then have the main ENS registry interacting with your resolver contract. And so this is something that you will have the private key to, that you'll have the ability to update, you'll have the ability to deprecate and change the information, and nobody else. But people are not going to necessarily know to go to your contract when they're trying to go to your website unless there's a centralized hub where all of this information is stored. So that's the point of kind of separating it out. But can I get your name? Junping. Any other questions? Yes. The question is, does everybody have the permission to access IPFS? So maybe you want to elaborate on your point a little bit more? I see. So the question is, for example, if you wanted to see the ownership of a certain URL or this, I guess, data that's on the IPFS, can you do that? So at least within the Ethereum name service, because there's a forward, I guess this is something that I did go through a little bit quickly. Because there's a forward and reverse lookup, then you can, yes, go both ways. It's not just a one-way. It's not just a one-way street where you put in the URL and then you're pointed to the purely to the equivalent of the IP address. You can also put in, for example, the IPFS address and then be pointed to the resolver contract or the address that this is supposed to go to. So in that sense, with the reverse lookup, you can put in, for example, the links of certain smart contracts or certain IPFS metadata if it's stored within the ENS registry to point to whatever address this is supposed to be relevant to. I think, but this is not necessarily universal. So you don't have, so IPFS in general is used for storage in a lot of different areas, and not all of the people who are going to be using it will necessarily be putting the IPFS links in their own resolver contracts. You can definitely use IPFS and not use the Ethereum name service as a place to store your IPFS link. You can store it, as we saw previously in the Smart Apes, in the Bored Apes example. You can store it purely in the contract, the Bored Ape contract itself, if you wanted to. Can I get your name? Mira. Is it cloud, excuse me? The cloud or protocol? It is a decentralized data storage system, and it is in the cloud, yes. Yeah. Okay, any other, yes?
Is there a backup in case like one of the systems is down for IPFS? Is there a backup in case like one of the systems is down for IPFS?
So IPFS itself is decentralized. So in a sense, the data is duplicated over many different machines. And so if any particular machine goes down, then you're okay. And there's other kind of systems beyond IPFS that does this Filecoin as well. Kind of has a system where you can, allow your own, if you wanted, laptop to kind of provide storage, and you get paid a little bit for the service. Yeah, I know it duplicates kind of the data across many machines. So if any particular one of them goes down, you're okay. I think if the overall protocol went down, that would be, or had some major bug or some major hack, that would be relatively problematic. I don't think people have per se a backup as far as I know, but maybe they are forward thinking and they duplicate it onto Filecoin as well. If they really care about the data being secure, they can do multiple services just to be safe. Can I get your name as well? Douglas. Okay. Okay, so I think we've covered at least the major points about the ENS and some good kind of extending information about IPFS as well. So good kind of forward-thinking questions. Thanks, guys. So we're going to move a little bit from the back-end discussion of ENS and Ethereum name service to a little bit more of the front-end discussion of this concept of crypto wallets. Crypto wallets themselves are these things, so they're digital tools, oftentimes applications basically, that enable users to store, send, and receive cryptocurrency securely. They typically come in the form of either software, hot wallets, or physical devices, cold wallets. Hot wallets connected to the internet, which make them easier to access, and cold wallets tend to be offline, and thus provide higher security and less susceptible to hacking and theft. I'll just get a raise of hands. Raise your hand if you have a crypto wallet currently. Actually, quite a few people. Okay. Maybe raise it a little bit higher just so we can get a little bit more. So maybe like about 10% of the class, more or less. So this is something that, yeah, if you buy or sell crypto, basically, unless you're doing it through a service like Robinhood or your bank or some ETF or something like that, you would be able to download a wallet like MetaMask or other sources either onto your phone or onto your browser if you wanted it to be a hot wallet. And this would be the primary way that you would have a piece of software that would manage your public-private key that would keep track of all of the crypto that you've got, all the crypto that's been sent to you. And then if you wanted to make some trades, this would be the way that you would kind of make these happen. So wallets, again, use cryptography to secure and encrypt private keys, which are necessary to access and control the cryptocurrency funds. So again, the key itself is going to be a very long sequence of numbers. For you to remember this would be more or less impossible. So to have a wallet to do this for you ensures that you don't forget one of the many, many digits in this and be unable to access or send your funds. Crypto wallets also allow users to back up and recover their funds in the case of loss or theft. Again, this is varying by wallet to wallet. They also generally will support multiple cryptocurrencies, which make it easy to manage different digital assets in one place. This is, again, why we talked about previously this idea of Ethereum needing these different standards, the ERC token standards, so that if you have a wallet that's going to be sending or receiving information, or at least keeping track of how many tokens you have, then they will all be kind of using the same interface. But beyond just working with the tokens within the Ethereum ecosystem, which are on the Ethereum blockchain, because there's thousands of blockchains out there, these wallets that all have their own chains, again, their own miners, their own validators, and perhaps different protocols, consensus protocols. The wallets are set up in such a way that as there's new cryptocurrencies that come out, they will be updated to be able to keep track of which currencies are out there. And if you have some currency associated with a certain public address, then you're able to, your wallet is able to kind of keep tabs for you and also for the other chains that you're sending information to, that you have this much currency. Again, some crypto wallets also offer additional features like within them natively, like exchange services, staking, or other decentralized finance DeFi integrations. And so as people built the software, they thought, okay, we already have a captive set of users, we might as well sell them some more other services. The different types of crypto wallets include desktop wallets, meaning if you have your own desktop computer, you can have an application that's just running natively there. You can have on mobile, so this can be a plugin, for example, for Firefox or for Chrome, that will store this information and allow you to interface these different Web3 sites and send money to them and interact with them. You can have applications that are purely on the cloud in the form of web, and of course you can have hardware wallets in the form of, you can have mobile phone wallets, you can have web wallets, which would be our kind of desktop browsers, and you can have hardware wallets, which would be something that you don't want plugged into the internet unless you're particularly deciding to make a transaction. So this would often be stored on something like a USB drive that you would just plug in once you wanted to you have your signature be applied, or to make sure that you have updated your ownership. Again, because the actual currency is stored in a decentralized manner, it's not like a typical wallet where if you break your phone or you lose your hard drive, that the money's actually gone. The money's not actually stored on the hard drive. Again, the hard drive or this hardware wallet is going to be storing your private key essentially. And so if you lose it and if you have a backup, you could just fine. If one gets destroyed, you have a backup hardware wallet with your private key on it, you're fine. But you haven't actually lost the money, because again, the money is stored in the whatever databases that are in these decentralized cloud systems. So again, within these different wallets, there's a varying kind of a set that have their own unique features and benefits. We'll go through a few of these. One of the distinctions we could talk about is this idea between a custodial wallet and non-custodial wallet. Custodial wallets are managed by third parties like exchanges, digital asset managers, or even custodial banks. So some examples of these can be Binance and Coinbase. And so instead of having a particular smart private key that you write down, instead they give you a seed phrase that you can access, that you can use to access your information. And if you lose your seed phrase, there might be some recourse for still getting access to your funds, similar to if you lose your password. Perhaps there's some way of getting an email to you. You can kind of set up, or at least different third-party managers might allow you to kind of lose your password and have some recovery mechanisms. But because they store all of your keys for you, if they're hacked or targets of theft, there's nothing you can do about it. You've basically given them the ability to hold these funds on your behalf. But on the other hand, they might be more liquid and easy to move because they are storing everybody's private key internally. They're able to quickly just keep, like a bank itself, keeping the money for you and giving it to you if you ask for it. They can be more liquid than a normal system, and they can, in fact, have lower fees involved because they can move things internally within the system without necessarily needing to pay gas fees or the exchange fees that you would get if you were purely moving through decentralized exchanges or decentralized marketplaces. So, okay, I'll kind of, go through these and then kind of discuss some of the interesting things. So non-custodial wallets, on the other hand, is going to be, the opposite of what we just discussed. In this case, we have users managing their own keys, both public and private. And they can either be hot or cold. So if you're storing your keys on your own device, on your own phone, let's say, that would be a hot wallet, but it's still not having a bank or having another company holding your keys for you. And again, if it's cold, you might have it on some jump drive or some USB drive. Again, this offers more control and security. One of the problems with the FTX scandal, if you guys remember this, was it was managing a lot of people's basically crypto bank accounts for them and moving the money around behind the scenes without telling them. And when they wanted to get their money back out, they couldn't. And so this is kind of one of the risks you might see in trusting too much to a company to manage your keys and your assets for you. If you have it on your phone, there's no risk of a company basically doing any funny business and stealing your money. Also, you don't necessarily need to provide these Know Your Customer checks. KYC stands for Know Your Customer, and this is something that basically prevents the money being used for terrorism, for money laundering, for criminal activities. And all of these companies like Coinbase, like FTX, when they get set up, if they don't want to be taken down by the government, they have to make sure that they're dealing with real humans who are not criminals. And so you'll have to provide certain identifying information, such as your ID card, a picture of your ID card, a picture of your passport, something like some kind of identifier, so that they can clearly link the account to a real human being. And so if you're doing something with just a non-custodial wallet, then these non-custodial wallets, because they're not central companies that are going to be managed by the banking regulations, they can allow you to kind of basically ignore these KYC checks. In general, though, if you do lose your key, you won't be able to access or restore your funds unless for some reason you have some duplication of your key, which we'll talk about in a bit. So in terms of, again, the safest option, we typically know that a cold storage will be the safest. No company can take your money. If you're storing your private keys offline, it's not plugged into the internet, your computer's not being hacked, and the data being read off of it, then you can be a little bit more secure. Again, if you imagine you have some keys or some bank accounts that have millions of dollars worth of crypto sitting in them, this is a very juicy target for a hacker. They could just hack onto your machine, read what your passphrase is. If you have it, read what your private key is if you don't have it encrypted in some way on your device. And so having it in cold storage adds another layer of security. In general, though, it's important to keep backups if we do have it in a cold system, because the wallet can be lost or damaged, and there's, again, no way to retrieve this. So if you have it on a USB and you lose it, your mom puts it through the wash, and then all of your millions of dollars is gone because you failed to duplicate your key. There's various types of these cold storage wallets. We have hardware, paper, and offline software wallets. When we're talking about the pros and cons of hot storage, so having things online, We see that most people, although cold storage is more secure, we actually see most people in the ecosystem going into hot wallets because they're just more convenient. People oftentimes will choose convenience over security in many different ways. Again, and hot storage is, for those of you who remember, is the wallets connected to the internet. They allow generally more quicker and easier access to cryptocurrency. You don't have to plug in your key each time physically and have it interact. You can purely just have it on your phone or on your desktop. They typically are going to be used more for small or medium amounts of cryptocurrency, so that there's less. Although they are generally secure, but if you have millions and millions of dollars, you might want to have some extra layers of security. If you're transacting in hundreds or thousands of dollars, you might be fine just doing a hot wallet. They're, again, best if used for frequently access funds, similar to a checking account, and is sometimes recommended to only keep a smallish amount of cryptocurrency in a hot storage wallet for everyday use. And if you have, again, large amounts of money, keep it in a cold storage wallet, because you never know for sure if these wallets have security flaws, have updates that are pushed to them that introduce new vulnerabilities or other things of this nature. In terms of on these online exchange wallets we talked about previously, again, these are typically provided by cryptocurrency exchanges like Binance or Coinbase that will hold these private keys on chain. And mobile wallets, again, are just applications that can be downloaded onto your smartphone and used on the go. To discuss a little bit more of these different hardware wallets that we discussed, or cold storage wallets, we have a hardware, which, again, physical devices such as a USB connector. We can have paper wallets, which are actually physical, like not just the physical hardware such as a USB, but physical copies of the paper keys might be written down, printed on paper, and stored or kept in some physical location. So they're not even digital at all. You can just purely have something that is the equivalent of a sticky note, but ideally hope something better that will allow you to access your information, and so nobody can hack it unless they have some kind of they take control of your camera and then break into your safe where this is stored, and then are able to find the information that way. Finally, there are offline software wallets as well. So you can have desktop wallets that are that you just keep this computer offline, although that seems a little bit bizarre these days. You can have computers, desktops, or even laptops that you just don't connect to the internet. You don't have the Wi-Fi turned on at all, and you can store the wallets there until the moment that you need to maybe very rarely connect it to the internet, and then start making whatever trades you need to make. And so that might be a little bit less likely to be lost than a USB or something like that. In terms of security parameters, there's different things you can do to keep your wallets secure. You can keep your wallet to store it in multiple locations if you have multiple backups. Again, you want to keep your software and operating systems up to date. If you have an operating system that has some bug that allows it to be hacked, then this is something that it might compromise the underlying vulnerability of any wallets you have stored on this device or computer. And finally, something we talked about a little bit about before, but we'll kind of discuss a little bit more now, is this idea of a multi-signature scheme. And this is a combination of a signing and verification algorithm where multiple signers will each have their own public and private key, and they can jointly sign a single message that results in a single signature. And this can be verified by anyone who also knows the message and public keys of the signers. And so to discuss a little bit about this multi-signature scheme a little bit in more detail, last time when I talked about it, actually I'll throw it to the audience if anybody has a good memory. What was the, any of the details we discussed of why you might want to use a multi-signature scheme previously in our previous discussions, if anybody has any memory of this discussion? If you're going to take a single signature and divide it up into many different copies that all need to be, or some combination of them need to be used, what is a good use case for that kind of technology? We have one guess. Yeah.
To the family situation, you like there's a file that you split up into like different family members so that only one can combine the keys that you have access to.
Yes. And is Douglas? Jumping. Okay, sorry. Okay, jumping. Yeah, so jumping is right. So I'm sorry, I got the names written down here. So yeah, so what we talked about last time is that, for example, let's say you are worried about passing away and you want to give your money to your kids, but you don't want to just have the single uh, signature kind of give it to any particular person because they could just steal all your money. So what we talked about last time is that if you have a little bit of trust in different family members or different friends, close friends of yours, you can each give them one of these multi-signatures, multi-signature keys, and if the majority of them come together to, in a trustworthy way, kind of use their keys to then access the funds and give it to your children, this might be a way that you can have some more faith in, the continuance of your, legacy to your kids. But beyond this, even just this kind of like dramatic, like passing away example, if you're worried about being hacked and you're storing your signature on many different devices, if you want to, in a sense, fragment the signature in this multi-signature scheme, if one device gets hacked and not the other ones, then the person who hacked this device can't per se use this single hacked device to access all of your funds. And so by, again, splitting your signature amongst many devices or many different companies, even if you're going to make them custodial, then in this way, you're going to have some ability both for hack prevention and also, in a sense, for recoverability. If you lose your own kind of single key yourself, but you've kind of given these different multi-signatures to fragments to many different, let's say, custodial wallets, then you can kind of ping each of them to give you the fragment of your signature, but none of them have the ability to access your funds on their own, and they don't even necessarily know who each other all are. So this multi-signature scheme is something that's kind of been introduced to add more security. If we talk about, is it worth buying this cold or offline wallet? Again, they depicts, depending on how you go, they can be expensive, but also they could be worth the investment if you're storing millions of dollars, right? Or hundreds of thousands of dollars even. And these alternatives to non-custodial wallets could be more affordable. I'll just make a few extra points here before we kind of finish off this topic. So although there's a lot of technology here within the kind of to make things more secure, we talked about cold wallets, we talked about multi-signature schemes. Crypto in its initiation was founded on this idea of security, cryptography, privacy, not trusting third parties. But what we see in the crypto space is surprisingly a huge desire by the general public who engage with crypto to basically give up as much privacy and security as they can in exchange for convenience. And so this is a little bit of a shock for the people who are building the systems in the first place, because they said, look, we're building these systems that get rid of the middleman, and now you're giving your keys to a middleman. Isn't that kind of strange? But in fact, as we saw with the FTX scandal or the other, just in general, these other wallets, people quite often are willing to give up their privacy in terms of convenience. And so the trick, I guess, for developers in the future is to make sure that we're able to perhaps develop better products and better technology that allows convenience without sacrificing so much security, or perhaps also just being aware that if you're trying to sell the world on how secure something is, you might only be interesting a very narrow market. A lot of people are still quite willing to use crypto without having so much security at hand. Maybe another point here as well is that despite the low levels of security that everybody else is doing, you might think twice and maybe back up your things in a more secure manner if you have significant amounts of money to lose. Are there any questions about our kind of discussion about wallets? Yes. So the question is your name? Asha, right. So Asher's question is the universal login that we talked about last week, which was this Ethereum standard that allows you to have a single identity across multiple decentralized applications, is that related to this recovery mechanism? I would say in general, no. So the custodial wallets that are managed by these third-party providers each third-party provider is going to have their own unique way of deciding to the degree to which they will allow you to lose your password and recover it. And in general, because their typical users are not going to be like, their average user is not going to be super like techie. It's not going to be an engineer. It's not going to be a software engineer. And they will basically probably use things that are more accessible, just like email, backups, things like of that nature. I think the universal login is something that's going to be more used by web developers, or in fact, it can also be built into a wallet itself, so that if you have a particular wallet and you access different websites, they might all say, oh, it's Asher. If you allow it to opt in to know that information about you, right? But that's something that's going to be more accessed by software engineers or by the people who build the app functionality into the things like wallets. Yeah, so the third-party developers do allow this recovery, are going to be something that they have their own system. I'll just say one thing about the seed phrase as well. So even some wallets that are not necessarily custodial will also have a seed phrase, which again is a combination of, I forget exactly how many, but something like 16 random words that would allow you to easily write it down, first of all, but also if you lose your password to some of these hardware or kind of desktop wallets or even web browser wallets, you might have a seed phrase to access this. So that this seed phrase is not only used for custodial wallets, and if you again kind of download something like if you download some of these other kind of common wallets, you might commonly be presented with a seed phrase to store somewhere safe in case you lose your password. Any other questions about the kind of wallet discussion? Yes.
Actually, I've got a question. For custodial wallets such as like Binance, Coinbase, and FTX, how do they actually earn their fees? Like if I were just to buy crypto and I were just to store it on their platform, would I have to pay like a fee?
I think that's a good question. I think they do have some fees for. They typically earn fees more as exchanges, right? And so if you're and also how these kind of third-party exchanges work, like Binance, Coinbase, and FTX, is that they are also ways to convert fiat currency, like Singapore dollars, into Bitcoins or Ethereum or what have you. And so this transaction between fiat currency and cryptocurrency is one way they can get some fees and get some income. Also, because there are exchanges, if you're between cryptocurrencies, if you're exchanging between Bitcoin and Ethereum or any other stable token or what have you, they also will collect some small fees from this transaction as well. Yeah, this will be their main way. They have other products as well, but this is, I would say, are their main two sources of income. And I think so because of this, their custodial services are a little bit more of a way for them to entice users to use the platform, kind of because they make most of their money from these other things. Just storing the money probably is not going to cost you anything, or storing the passwords. Yeah. Your name? Kaisian. Okay.
I have a second part
Yeah.
of the question. Is that, in this case, since they're earning fees similar to how banks earn fees by having forex exchanges, then wouldn't, in this case that you mentioned FTX, wouldn't this kind of accounts be slightly worse than the bank account? Because the bank accounts are insured by the government. Like I think in Singapore it's like 75,000 Singapore dollars. But like companies such as FTX are not regulated, so like, a lot of people lost their money.
So the question, yes, is if they are functioning like banks. In the example given was that banks might make fees on foreign currency exchanges. The fact that these custodial wallets or centralized exchanges are not insured by the government, isn't that worse? I could say, yes, but also you can't use a bank to transact cryptocurrency, right? And so, so because they're not insured, if they are hacked, people generally just lose their money. Sometimes the company might have some guarantees to say, if we don't go bankrupt, and you got hacked, will try to give you your money back. In FTX case, they are going bankrupt, but they're still, because they're a company and they got put into the hands of certain bankruptcy managers, you're gonna either get a percent of your money back, or maybe the bets will pay off that they made early on, and you'll get all of your money back eventually. But right now, it's just stuck there and it's not liquid, right? Yeah, they tend not to be insured by the banking regulations. So maybe that's something the government should force them to sign up for, is the banking insurance to kind of ensure the minimum balances. But currency, yeah, they're not backed up by banking insurance, deposit insurance. Okay, good questions. Other, yeah.
As for the cold wallets, right? You mentioned that it's not a private keys online. You mentioned that it's not a private keys offline for cold wallets. So, but then in order to perform any sort of transactions, are there any like online addresses associated with them?
So the question is, for the cold wallets, you store the private keys offline. Are there any online addresses associated with them? Maybe elaborate a little bit more, just like.
Because if you want to transfer it or whatever through these cold wallets, there must be some sort of way for the blockchain to interact with the cold wallet.
Right. So the question is there a way, if you want the blockchain to interact with the cold wallet, how do you do that? Are there any guesses as to answer this question? Because the cold wallets store, let's say, your private key offline, if you want to trade currency, what do you do, or what kind of information is kind of online while you have a cold wallet? Your public key. So the currency, again, as I said previously, is not stored inside the device of the cold wallet. The cold wallet just stores your password, basically. And so the currency is always stored at the public key address, and it's always going to be online. And so if you want to send money from your address, you need the password. And so the cold wallet will just store the password. If you do want to send the money, then there's different things you can do. One of the things you can do is, if it is a cold wallet that you plug in, you can just plug it in, and there might be some kind of software that will read this information for you. If it's simply a TXT file that has the string of your private key, you can read that off, or you can copy paste that, or you can plug it in temporarily to a computer, copy paste it, have it or have a wallet software that is set up to use these cold wallets, so that once it kind of gets the information from your cold wallet, it will let you do whatever transactions you want to do. And then once you take the cold wallet away, it'll hopefully erase whatever private key it had on the device while I was making those transactions. Does that answer your question? Any other questions about wallets before we finally move on? So I'll encourage you all to, this is not going to be part of the class, but I do encourage you all to, in the next week, try to go online and download a wallet. This, you can generally get one for free, and this will just basically be if you want to, in general, use any kind of Web3 interface at all, it's important to have a wallet set up that will give you a certain public key address. And you won't necessarily need to trade currency or have currency on the wallet to use it, but this will kind of show you, dip your foot into the ecosystem of what it looks like. So hopefully, after you go through this class, you'll have kind of done a little bit of this firsthand experience. But with that, again, any final questions about wallets or ENS before we move on? Okay, for now, we're going to discuss this next kind of 45 minutes, hour. We're going to discuss this concept of smart contract design patterns. So we're a little bit kind of jumping from different from item to item here. So ENS was more about the back end of the kind of web interface of the Web 3. The wallets are kind of the front end of Web 3 and how you interact with it. And smart contracts, again, I guess, are the middleware. This is the actual security of the smart contract design itself. We call these design patterns, but these are basically ways that you can, these are kind of ways that people have developed over time to both make smart contracts more secure, but also just add functionality to them and allow them to do more things. You can't always treat smart contracts exactly the same as you treat a typical software project, because of the features of immutability, because of these features of decentralization, where you don't have direct control over it. A few additional pieces of ways of interacting with the smart contract and designing them in ahead of time have been built up. And so the 5 that we'll discuss now, the 5 big categories here we'll discuss at least, are authorization, action and control, life cycle, maintenance, and security. And this is going to be relatively important. So pretty soon, in the next couple of weeks, I'll be giving you guys your project, your kind of project definition, where you're going to be designing your own smart contracts from scratch. So the information with your team, and so the information here is going to allow you to design more complex web applications that are going to allow you to do more things. So this is going to be pretty important for your final projects and for any smart contract decentralized applications that you decide to design. So starting with authorization, we have this problem of ownership. Just previously, in terms of the ENS server example, we have this idea that if you own a particular website, you have the registry that keeps track of what website links to what domain. But we wanted an ability for a particular owner of the smart contract to be able to update the information and change it over time. And because we have this all this information online, we need to have some way that you can own something that's kind of stored in all these different distributed areas. So the problem with ownership, again, is that because any party, can call a contracts method, we want to ensure that still the sensitive information in the contract can only be executed by the owner or by certain verified people. Again, because you're putting these contracts online, anybody can call them. You want to make sure that you can call them, but certain functions, but not everybody else can call them. So the solution is to store the contract creator's address as the owner of this contract, and then restrict the method execution to be dependent on this caller's address. So this is another important reason to store your information in your wallets, because if you lose your wallet, then not only do you lose your money, but you might lose access to the whole website that you built up, because it will store the ability to send messages from that wallet in the first place. So this is a piece of Solidity code. We're going to be going through this kind of examples as we go through the rest of today's class. And this is hopefully where we'll see where this is showing up. So as you can see, this contract has is owned, and we have this piece of information, which is the owner. This owner information is going to be set as public and is of the type address. And so having this concept of ownership allows us to do several things and to kind of work with it in interesting ways. So one thing you might do is you might want to transfer ownership. If you get tired, if your friend or whatever, friend is running it, he wants to retire, he gets a stroke, what have you, he wants to transfer ownership, you might have a function built into your code that can transfer this ownership from a particular owner address to somebody else. If you have a modifier, if you want to put a modifier on any of your functions that say only the owner, let's say, can interact with this, then you can build this in simply by saying we're requiring that the message.sender address is the same as this owner variable that we initiated. I think we discussed this previously, but I think there might have been some confusion given the questions from last week, kind of after class. This keyword of message.sender or message.amount, we'll see this kind of keyword come up repeatedly. And within Ethereum, this MSG message keyword is used to capture the information about the person who's interacting with the contract. And so the .sender variable is basically indicating what public key address is sending the message or is trying to interact with this smart contract. And so for this modifier, if we're requiring that the message.sender equals the owner, then that's going to be the restriction that allows us to kind of keep certain functions gated. And then we have this underscore keyword, which I kind of went through a little bit fast last week. This underscore keyword is what is going to allow us to have modifiers on our other functions. And so moving on, if we have our function.owned, this is a public function that's basically setting the owner to be the message sender. And so again, this is going to be our, because again, this is the owned contract, this a function that has the same name as the owned contract is going to be what runs the first time we initiate this contract. And so this is going to be setting the owner to be the message sender as soon as this contract gets run for the first time. Again, we have our transfer ownership function, and this is going to be what we allow only the owner to interact with. And again, we're requiring the new owner is going to be not the same as the person who's interacting with it, and then we'll change the ownership using this log ownership transfer function and set the owner to be the new owner. So again, this ownership criteria we'll see kind of in future cases why this is so important, but this is one way we can kind of interact with the setting and changing of the ownership of a contract. In general, when we want to do this access restriction, as we talked about, by default, the contract method can be executed without any preconditions being checked. That's the default setting. But if you have some desire that the execution is only allowed if certain conditions are met, such as this, only the owner can access it, or only certain people, or people can access it at a certain point in time, or only the function will only run and consume gas if people are putting in enough money, so like a vending machine, you have to put enough money for it to do something. Then this is all things that we can kind of gate the ability to interact with different methods by having these different access restrictions. So again, just to reiterate, you might want to control the time that somebody interacts with something. You might want to control who is interacting with it and other transaction information. And you might want to kind of limit it by the amount of money or value that they're sending. So our example here, we have our access restriction contract, and this is going to be extending the owned contract that we just discussed. So we're going to have some of this, it's going to inherit the methods here. So we have in this case a new variable called creation time that's set at now when the contract is initiated. And we're going to have our modifier that says only before our integer of time. And it's going to require that the time that the modifier is checked is going to be less than a certain time that you indicated that something has to happen before. And then again, we use our underscore to indicate this is going to be our modifier. Similarly, if you want a certain function only to be accessible after a certain point in time, you can just check that the now keyword is going to, which again picks up this, as you can see, it's in purple, is picking up the kind of latest timestamp in the Ethereum blockchain. So this is where this now comes from. If you want to check that the time currently is greater than a certain time that you set as after, you can do that as well. And then finally, you can have your modifier that only certain people can change this. Sorry, not finally. So anyways, so if you want to modify only by certain people can change things, not just certain times, then you have, you set the address of the person who can change it or the accounts that can change it, and just set the message sender needs to equal that address or one of those addresses that you set. If you want to have some other condition, you can specify. So previously here we had as our previous conditions, the message sender needs to be the same as the person who is allowed to interact with it. We previously had these Boolean conditions of the time is after or before a specified time, but you can be much more creative with this and arbitrary in this restriction or allowance of people to interact with your methods. So you can think of any particular condition and have it be set here and just require that the condition be true, and then that can be used to modify it, the method. One common one we'll see is the minimum amount method modifier, and you can just set the minimum amount. And again, we use this message.value keyword to check how much money is being sent to the contract by the person interacting with it, and it must at least be a certain amount before our function will go. And so seeing all of these in practice, we could have some function f that's payable, so it can pay money out. But we're going to have certain restrictions. It will only happen, this function will only be allowed to run within 1 minute after creation time. And so we can't create the contract and have it immediately be run. It can only be run by the owner, so nobody else can extract money, let's say, from this. And we're only going to be running this function at all if 2 Ether are being sent to the contract. And if and our arbitrary condition here is that the balance of the sender is greater than 50 Ether. So this is another condition that you can check by, again, checking that you can use the message information to see the public key of the sender, but also check their balance as well. And because this is native to Ethereum, if it's greater than 50 Ether, then that's going to be the only time that we can interact with this contract. And then if all of these conditions are met, the function of whatever some code will execute itself. So that's simply just authorization and restriction. Access and control is a similar problem. In this case, we have a application, let's say, that implicates we have different behavioral stages and transitions. So, for example, if you have a simple, let's say, prediction market, you want separation in time between the time the prediction is getting made to the time that the bets are locked in to the time that the event is updated in the system and the time that the money is paid out. So by having these different temporal phases in the thing you want to do in your business process, you'll want to use this state machine architecture to update the ability of the contract to only do certain things at certain states in time. So you can think of any kind of online application you might envision and the kind of different sequences of things that need to happen and how you might want to lock certain functionality at certain points if there's too soon or too soon or past that point in time. Are there any questions so far? Okay. Again, this might be a little bit kind of tedious, but again, hopefully this will give you an overview of the different things that we can do, and it'll be useful once you start building your applications. So again, we apply this state machine model to represent the different behavioral contact and contract stages and their transitions. And this helps also to break these complex problems into simpler steps, and it can be used to represent and control the execution of the flow of a program. We're going to begin using this if we have a contract that has several stages during its life cycle. We'll show you some examples. And this, the functions should only be accessible during certain stages. And these stage transitions should be clearly defined and not preventable for all participants. In terms of participants and collaborators, the first participant is going to be the person who implements the contract that will transition from stage to stage, while other people might be the contract owner or other interacting users who are still able to initiate the stage transition either directly by if they have access to say, okay, let's go to the next stage, or indirectly if some timer runs out, for example. So let's see. I'll just kind of give some I'll give some examples of this before we go through exactly how it's implemented. So one example might be an election. So if there's a phase in time where certain proposals are put on the table, then there's a phase in time where certain people need to vote on the proposals, and then if you don't show up in time to vote, it might move to phase 3 where the votes are counted and the winner of whether the proposal wins or loses is announced. Another example of a kind of a state machine with a phase transition might be if you are setting up a, let's say, a bidding system for a contract. Your company or your government wants to find people who are going to build something for it, and you want to collect the best quality for the lowest price. You will have the owner of this auction, essentially, or of this request for proposals will put out the proposal. There will be a timed period where people can put in their bids, and these hopefully will be in some sense a secret. And then once this time runs out, nobody can put in bids anymore. It'll go to phase 3, where the people are perhaps checking the background of all of these bidders is checked. And if they meet the requirements, let's say they're registered with the government and qualified to do the work, then the one with the lowest bid will be chosen as the contract winner, and then if they do a good job, they'll get the money put into their account. And so these kind of phases within the system is something that you might want to build into your application. So how stages are generally represented is with these enums variable. So it's very clear which step you're in as you're walking through the system. So if anybody is kind of interacting with a smart contract and trying to say, hey, what stage are you in? It might be able to kind of clearly say, oh, here's the stage. And you're not going to get confused by accidentally going into stages that shouldn't be. If you only want 4 stages, but you're just using integers, you accidentally make a mistake and now you're in stage 6. You might be have some bugs. So by having enums is going to be a little bit more enumerated lists is going to be a little bit more easy to keep track of which stage you're in. Finally, you also want to use these access restriction patterns that we just talked about. So only certain people, for example, might put in bids. Only certain people, sometimes there'll be a timeout in terms of the phases, but maybe the owner will want to just push something to the next phase. And then also one final important point here is that the stage transitions have to happen through function calls. What this means is that unlike a typical program, it can't just check its watch and say, okay, enough time has passed. I'm now switching from the voting phase to the counting of votes phase. There's no automatic execution of any of these contracts. Although we say the smart contracts are smart and they execute automatically, in reality, you need to have somebody call the function and pay the gas fee in order for the contract to do anything. And so move from stage A to stage B. And so this is something that we'll see is quite important. It's a little bit counterintuitive because we generally talk about smart contracts as being automatically executing. No, in reality, you need somebody or something that's going to ping it and pay the gas fee and have it move to the next stage. So if we have this contract here, a sample contract for a state machine called a deposit lock, we have here our stages enumerated list, and we can name the stages here: accepting deposits, freezing deposits, and releasing deposits. So we have, when we set it up here, we set our initial stage here as the stage accepting deposits, and we here set it as public so that anybody who wants to check what stage the contract is in can easily query it and see what it is. Again, the creation time is set at the creation time of the contract now, and just stored as a piece of information. And then we have our balances variable that's going to be mapping different addresses to different integer amounts. And then again, this will be a state variable, but in this case, it's not public. In terms of the modifier here, we have it that we can create a modifier that says something should only happen at a certain stage, and then this stage can be specified when the modifier is placed next to the function, and simply say the stage state variable that's specified, of course, here has to be equal to whatever stage we're specifying in the modification. And so we have our timed transitions modifier as well. So we can say, for example, if the stage is at accepting donations, and the creation and the time right now in the blockchain is currently 1 day after the creation time of the contract, then we can move to the next stage. So it'll go from accepting deposits now to freezing deposits. Now, if the stage is freezing deposits and the time that you're interacting with the contract is greater than 8 days past the creation time of this contract, then we can move to the next phase, which again is now freezing deposits to releasing deposits. We can build in here our next stage function, have it be internal so that only this internal smart contract can interact with it, and say the stage is simply going to be the integer of the stage plus 1. So this next stage function that we're calling here, we're just defining here, and this is how we can implement it. Again, just to be clear, this enumeration variable has a few interesting properties. So first of all, you can just simply list the names of what it is, and if you want to go from one to the other, you can do it by converting the stage to an integer and just incrementing the integer and putting that into your stages enumerated list, and then set that as you update the stage that you're currently in, which again is your state variable. So we're updating our state variable here. And finally, we have our deposit function that's going to use some of these restrictions. So in this case, it's public, so anybody can call it. It's payable, so it's going to pay out or allow money to be paid in. It's going to have timed transitions as our modifier, and it's going to happen at a certain stage. And so we have, again, stages that accepting deposits is going to be the stage that it can happen in. And then the body of this function is that the balance of the message sender will get incremented by the amount of money that they're putting into the account. So again, we had our balances mapping here that basically is keeping a certain amount of money in the contract under the name or under the public address of certain people. Finally, if we're within the withdraw stage, again, anybody can call this, but it has to happen at the stage of releasing deposits. In this case, the balances of the message sender gets put into this integer amount. Then we empty the balance of that sender, and we transfer that money back to the person who is calling the contract. So it's a very simple contract. It's not doing very much. Of course, it's just putting money into a contract, locking it for a certain amount of time. In this case, a week, and has 1 day of period beforehand when nothing can get done, just to make sure there's no bugs in the program. But you can imagine more interesting things being done with this. If you're having people lock in their money, maybe you're going to do something with that money. You're going to give them some kind of interest in exchange for locking their money away. This might be a way to start to implement some kind of decentralized lending or borrowing protocols. And then by having these timed transitions and keeping track of who is putting the money in and who's taking it out, this might be a way to start to do some interesting things in the decentralized finance world. This is a very simple example, but you can see how this might be relevant. Any questions so far? Yeah.
So the order of the modifiers on the functions matter.
So maybe elaborate a little bit more.
So if you see the withdraw function, the first modifier is time transitions, and then we do add state. So are these modifiers executed in the order that they're being specified? And I think it should in this case, otherwise it won't go to the next stage unless and until the time transition modifiers.
Yeah. So in general, you're exactly right. So as the sequence of the modifiers does, it matters. So if one fails, then it will just not go to the next one. So all of the modifiers will have to be true for it to work. Okay. Next, we have our commit and reveal pattern. And the problem that this is going to be, I'll just discuss and then kind of elaborate. So the problem is that all data and every transaction is publicly visible in the blockchain. But an application scenario sometimes requires that contract interactions, specifically some submitted parameter values, are treated confidentially. So our solution to this is to have a commitment scheme that ensures that a value submission is binding and concealed until a consolidation phase runs out, after which a certain value is revealed and is publicly verifiable that the value remained unchanged. And we're going to do this by hashing it with a secret nonce or a salt. So, okay, so I'll give you a simple example and then I'll give you a more complex example. So our simple example here is going to be a rock, paper, scissors game. And so what this commit and reveal problem means is that let's say you want to play hypothetically for some reason rock, paper, scissors on the blockchain. Of course, because things are timed in a sequential manner, one person might play their hand or submit their hand and some time passes, and another person submits their hand. If you're playing this game for money, you don't want the second person to be able to see what the first person did, because they could easily just play a winning hand. So if somebody plays paper, the other person can just play scissors if they see that the first person put paper into the smart contract. So, but also, So that's one piece of a kind of important problem. You don't want the person to see what you did, but also you don't want the person to back out of what they did. If you put in paper and someone else did scissors, or you put in paper and someone else did rock, you don't want the person who initially put in their let's say play to change it later on and to somehow get out of it. And so because of this, we call this being a commitment. You commit to whatever you're doing, but it's committed in a secret way, and then it's revealed later. Again, because we talked about how every transaction and data is visible in the blockchain in some sense, when you're making a commitment, you want it to both be secret and in a way that someone cannot back out of this. And so again, the way you do this is by hashing the information and then revealing the hash later. So what this looks like for our simple rock, paper, scissors game is that, let's say you want to play the move paper, hypothetically. You'll take your hash function, you'll put in paper as the variable, and for salt, you choose some random information that only you know, but you can easily remember, you store it somewhere, to add on to this paper variable, and you hash this. And by hashing one of the three moves, which everybody will know, with some salt that nobody will know, you'll get a very unique hash value that basically nobody can understand, not even the smart contract itself. And this will be stored as the move that you made. For player two, they'll come along and say, okay, somebody else played the first move, I'll play the second move. I'll play, let's say, rock, because I have no idea what this person played. It's just some random jumble of information. And then again, I'll add my own unique salt. So all of these salts are different. Each person has their own unique salt. And so user two puts in their own salt to the nonce, their own random data into the information to be hashed. They hash it, and this information gets stored. So all of this is happening at phase one, the commit phase. Once the commit phase has ended, let's say it ends because now enough players have submitted their plays, or maybe it times out, however we want to transition it. Now we can kind of close the commit phase and open the reveal phase, and now it's time for the players to see who won. So let's say in this case, user one will say, okay, I want to show the world what I played. I will say, here's the hash value that I put in previously. Here's the unencrypted value of what I played, which is paper. Here's the clean text version of my move. And here's the salt that I used to combine with the clean text to get the hash. So these three pieces of information prove that I'm the person who put in this move at that time. And then user two will do the same thing. If person two, however, sees that person one played paper, and they prove that they played paper, let's say person two will try to change their move to scissors because they know they're losing. Scissors will beat paper, but they put in rock previously. If they try to say that they played scissors, and it would basically be almost impossible for them to find a salt value to add into this move that will deliver the same hash that they originally put in. And so this basically, if they try to say, oh, actually I played scissors, they'll get a different hash value, and the system will reject it. So the point of this is that, I guess in this case, user two lost the game. They know they lost the game, and so they might not even actually put in any information at all. I mean, they might be truthful and say, yeah, here's, I put in salt, I put in rock. Here's the salt that I used. Here's the proof that I put in rock. They might reveal their move, or they might know they're losing the game and not reveal the move at all because it would cost them some gas or something like that. And so there could just be some timer at the end of the timer. If the user two didn't put in their information, then user one wins by default. So this is a simple example of how we would want a commit and reveal. A more complex example, because maybe putting a rock, paper, scissors on the blockchain is a little bit childish, you might say, a little bit simple. A real example that I just previously talked about is if you're doing your request for proposal and you want different people to submit a bid, you want people, you as the company or as the government want the lowest possible price from from a qualified person that you can get. And so in any of these bids, you don't want people to know what the other person was bidding. You want them to have some doubt about it. Because if they see that somebody else bid $1 million, maybe they'll bid 1 million minus $1, you know, and so they'll try to keep their price as high as possible. By keeping this information secret, you can kind of also verify that they're not undercutting it below what they can actually do the work with as well. So there's reasons why you would want to keep the bids secret while you're getting them. And then once enough bids have come in, then you can have people again reveal their bids, and hopefully they're the one that has the lowest bid and they win the contract. Another thing you might want to do with this, if you have some kind of secret ballot or secret votes, you might want to have everybody vote secretly ahead of time, and then once all the votes are in, reveal them later. So how this kind of, are there any questions about why we want to do this, or the conceptual understanding of how this is implemented? Okay, I'll dig into the kind of example then. So we have our contract now called commit reveal. We have our commit that's a struct variable, and we have a string called choice, a string called secret, and a string called status. We also have a mapping of addresses to commit, and this is just a public variable that has well, I'll say this again. This is a mapping between the address of a particular player, the public address, and then essentially the hash value of what they committed, the secret information, the secret code that they put in. So this kind of information. And this is stored as a 32-byte sequence. And this will be stored as user commits. We'll have the event called logging a commit that will just say, here is the secret hash, and here is the address, and we'll have a reveal that will have the hash, the address, the string, which will be the clear text, and the string of the salt that they used. So we have our function commit reveal again. We're so instantiating this contract. And then when we have our commit function, we are putting in this 32-byte hashed value that we're calling commit. This is public. And then this is returning that it's a success. And for this particular user, we're going to store in the hash map, we're going to store this user address and the hashed value of the information they stored in the contract. And then if the user commit status length is not 0, we're returning false because this implies that that secret has already been stored. And if it doesn't return a false, then we're going to return it as true. All right, so moving on. So if this doesn't return false, then we keep going. We have our user commit.status is going to be equal to C, indicating this committed. And we're going to then log the commit, kind of emitting this information with this event keyword that here is the hashed value as coming from this sender, and this is going to finally return true for this commit function. That was the committing side. On the reveal side will be once you've moved from your putting in the play to revealing the play, you have your reveal phase. So you put in the clear text of what you actually played, so rock or paper or scissors. You put in your secret, which is the nonce. You put in the secret extra information, and then you put in the hashed value that you got with this, and this should return a success or failure. And so we have our user commit variable that we're that we're checking your from this sender what was the information that they hashed, the hashed information that they put into it. This was their commit. We have our bytes status. So we take our user commit status, and if this byte status is greater than 0, we're again returning false because this choice has not been committed before. So this is how we're checking if this secret hash value has already been put in there. If the byte status of this entry is R, then we can return false because this information has already been revealed. But if on the other hand those things don't trigger, that we can say, in this case, we're going to check that the hash, in this case we're using CAC 256, if the choice, again, this is a clear text, and the secret, if we hash those two together, and this does not equal the hash value that they previously put in, then again, we're going to return false because the hash value doesn't match the secret hash value they committed. Finally, after all of these checks have been made, we'll update the user choice to the true choice it is, whether it's rock, paper, or scissors. We'll update the secret to whatever secret string they used as the salt. We'll update the status to be revealed, and then we'll log this information to say this hash value sent by this person was in fact this secret play using this secret salt. And so once all of those are updated in the public state variables, then this overall reveal function can return true. In our trace commit function, again, we're taking address, commit the secret hash value. It's going to be public and viewable, and it's just going to return the choice and the secret and the status. And because this is a view, this is not going to be changing any of the variables, it's not going to be updating any of the information in the contract or on the blockchain. This is purely just getting information from the contract. So this saves us some gas fees by anybody calling this contract by calling it a view. And so we have here our user commit, this kind of a local variable. And so this is going to just be going into this user's commits struct and looking at the address of the person interacting with our function here and the secret information, the hash value that they put in. And if this status is revealed, then it's going to return what the choice, secret, and status of this person already is. So these are some of the functions that you might want to use when you're building in any of these systems into your commit and reveal system. As you can probably see, this one doesn't have the phases of the state machine built in that we previously discussed. But by putting these different things together, you can kind of make these more complex business processes that you might want to do for your own applications. Any questions about commit and reveal or previous things?
I was wondering whether there any real life scenarios or use cases that's currently used commit and reveal, because for state machine you mentioned that many protocols we can actually use like for the real life scenarios. Yeah, so I was wondering for commit and reveal what like real life scenarios and use cases.
Okay, so I'll open this to the class. So I gave a couple examples. Does anybody remember what are some real life scenarios of commit and reveal that we might see implemented into a smart contract? Yeah, I can get your name? Sneha. So yeah, Sneha said the examples that we gave in class are if you're bidding on a contract, you want people to put in the bids, you want the bids to be secret, you want the people to be honest about how much it will actually cost them to build a house or whatever. Then we want that information to be secret, we want to get as many bids as possible, we don't want them to be strategic about knowing what each other are doing, and then once that phase has completed, then we want everybody to say what their bid actually was and also not back out of it. Because once people start revealing the price, if you ended up being the lowest bidder, you might double your price because you say, I can still double my price and make a lot of money. But that's not the way you wanted the bidding system to work out, right? So that's one example. We also talked about voting, where if you want to have a secret ballot and have people, again, not game their votes by what other people are doing, then this might be a way in which you again, have everybody put in their votes secretly at one point in time and then reveal them at another point in time. Of course, it's not so simple as a normal kind of paper ballot because people will still always have to, in order to reveal their vote at all, the individual will have to ping the system and say, this was my vote. And so if they really wanted to stay secret forever, they don't have to reveal their vote. But this might be one way that you implement a blockchain voting system. Can anybody think of another example for any participation credit of a commit and reveal system that they kind of thought of where this might be useful?
Like a lottery system.
Okay. Maybe elaborate a little bit.
Maybe they have like a number that they don't want other people to know at first, but to verify that it actually matches the one that was chosen.
Sure. So it's perhaps something like that. So a lottery, if you don't want other people to copy your guess or your lottery system, maybe a lottery is a little bit less likely because the numbers, a little bit, there's less game theory around why people will want to know what your guess is, right? But let's say it's like estimating the number of marbles in a marble in a jar of marbles, right? Or some other kind of game like that, where you don't want other people to know what your guess is, and then maybe if you're the closest, you get the money, right? And so that might be one reason. Maybe a similar thing is prediction markets. If you want people's predictions to be less correlated, if you want them to be more based on their own information and not have this problem of high certainty just because there's convergence around what's popular, then maybe that's another reason you'll want to separate the commit phase from the reveal phase. Any your name as well? Quite Xiang. Any other, any other ideas of potential ways this commit and reveal system can be used? Yes. Auctions. So maybe elaborate a little bit more.
When you basically want, you shouldn't review yourself, and then when you actually win the bidding, you track.
Right. So this is a very this is kind of a similar context as this kind of contract bidding system, but yeah, auctions. Yeah, gonna get your name? Len. Okay. Any final guesses or contributions? Okay, moving on. Oh yeah.
Actually, I have a question about this commit and reveal system. Is there a way to make it more convenient? Because now the user has to store the salt themselves. Can the smart contract store the salt? But then like through like a private, using the private signature, you can like hide the salt. So that only this person like call, when they call with their private signature, then they get the salt that's been assigned to them. Then they just pass the hash value to them.
It's potentially possible. So if you have a certain internal variables that you kind of specify can only be called from inside the contract, and then you have a modifier, let's say you store some mapping. Right now we have a mapping of hashes to addresses, right? But let's say you have a mapping of addresses to salts, then and you make this mapping a variable that can only be accessed from inside the smart contract itself, and have a modifier that to access this you have to be the person who is the user. Potentially you can do that, but I think in some sense, because you are still storing the information in a non-encrypted format on the ledger.
Is it because the salt, like the result of the function call is actually stored on the blockchain, right?
Yeah. Not just the result, but like the variables itself, like the state variables themselves. So like when I say result, like certain things are returned, but besides that, like some of the things you might be doing is updating the state variables, and this is stored in some sense in clear text on the ledger.
So you can use the private modifier.
You can use private modifier, yeah, but you still might be a little bit wary about who can access it. If you're really worried about like the validators having access to this, if the people who are running the servers having access to it. Yeah. Any other questions about commit reveal or other design variables? Okay. I think I have time. Okay. So life cycle is going to be somewhat different. So a smart contract is deployed. Once a smart contract is deployed, it exists as long as the network exists. But if let's say the auction ends, the contract's lifetime is over, you want to make it possible to destroy a contract and stop it from operating. So if you set up a new auction, you don't want people accidentally sending money to the old auction and getting it locked there, because then they're going to think you're like a bad auction operator. You're stealing their money or doing something weird. And so the solution to this is to use a self-destruct call within a method that does this preliminary authorization check that only the authorized, let's say, auction creator can invoke it. And then whatever ether is locked into this contract gets stored to some designated address that you provide as an argument, and the storage code is cleared from the current state. And so again, this helps us get around the problem of a mutability, imagining that contracts are going to be floating around there forever. There's now actually a self-destruct auto-included of function that you can just in this case, if we're using the destroy custom function, we have it that only the owner can call this a function, and then with this kind of insolidity kind of included function self-destruct is called, and you're specifying that the owner in this case is the one who the money that's left in the contract will go to. So when I say money left in the contract, remember that from our past examples that the every contract both has a public address and the code, and also, like any other public address, it has a certain bank account. It has a certain amount of ether in its bank account. And so when you're destroying this contract, there's an automatic ability for you to take whatever ether is stored in this contract and send it to whoever you indicate. In this case, the owner of the contract. If you want to send the money to somebody else, you can write another function called destroy and send that simply puts in the recipient of who you want the money to go to, and whatever money is left in the contract, once you are finished with it, will go to that recipient. So a similar problem to self-destruction is this idea of deprecation. Let's say you want to update a contract. This happens when some temporal, this usage scenario requires a temporal constraint defining a point in time when the functions become deprecated. I mean, that's the goal, and our solution is to just define an expiration time and apply modifiers, as we discussed previously, in the function definitions to disable functions once their expiration date has been reached. And so this is a little bit similar to destroying a function, a method once you're done. This is like destroying a contract, but instead we're just disabling functions once their time has come. So for auto-deprecate, you can see this is a function we're doing. We're putting in our unit of days, and then the state variable of expires just gets set as the number of day now is being the time that, again, this auto-deprecate contract was launched, the number of days that you put in, and then you multiply it by this unit carry word of 1 times days, so it's just stored as a time. And so this is going to be then stored as when the auto-deprecate triggers. We have our expired function that in this case is internal, but it's a view, and this is going to return whether or not we're past the expiry date. We have our modifier will deprecate. In this case, it requires that something is not expired. We have our modifier when deprecated that says something can run if indeed this expiry date has been passed. And in this case, we have our deposit function that says, our deposit function that does something, but in any case is only going to be allowed before the deprecation date, and then our withdraw function is only going to be allowed after the deprecation date. And so this is similar to our state machine, except instead of having distinct phases that this is checking, this is just automatically disabling or enabling even certain functions at certain times. As you can see, this code is not set in stone. It's not like a library that you can copy and paste. This is just ways of that people have kind of come to that's useful for kind of going through to kind of put in this different functionality to help with either temporal constraints, or again, if we think certain things should not be done at a certain time, we'll automatically deprecate them. In terms of maintenance, one of the things that we want to do is make sure that our we don't put up, we can debug our code or add to our code or do all these interesting things in a way that still works with the fact that the contracts are immutable and they're forever. And so because, again, this contract and its logic data are usually kept in the same contract, this keeps a lot of close entanglement to them. As you could see previously, we had all these contracts and they had all these like state functions. If you want to deprecate the entire contract and have a new version of it, but keep the data, you need a way to loosely couple the data from the contract. If people put in their bids to an auction and you want, or a game, they're playing a game and they want to keep playing the game, but you have up to the game, you want to keep track of everybody's data, or everybody's ownership of the items they have in the game, even as you update the contract or the software that runs the game. So how you do this is with data segregation. Once a contract is replaced by a newer one, the former contract must be the former contract's data must be migrated to the new contract version. And so we do this by decoupling the operational logic and the data into separate contracts. So this is going to be mimicking, if you've ever done other kind of software engineering classes, a layer design where we have a logic layer and a data layer. And in this way, we can design the storage to be very generic so that even as you're updating the logic layer, you're updating the game, it can still access the data that's stored in the data layer without too much kind of hard coding of how the data should be read by the contract. And you can generally do this with the help of these getter and setter methods. And so, so what this looks like in our kind of overall understanding is we have in this case, our get unit value that you put in some key of a different contract. Let's say this will be getting the information from our data layer contract. So you put in the address, the public key address of that contract, and it will return whatever information you want it to. And then you can update the storage of whatever data you have here into your key. Again, this is your data storage contract, your layer. And in terms of setting it, if you have your logic layer is calling this function, it sets the key that of the logic layer, it sets the value that you want to store, and then you update this storage with a certain key at a certain value. So by having this data be segregated, this is one way that you can do it. I think I misspoke also quickly here. So I said previously this might be the address of the kind of contract that's calling it. I misspoke. So in this case, this is going to be just a very generic data storage, basically a hash map. And so as part of making it generic, you're making it so that you can just put it, the logic layer should be smart enough to just say for any given key, no matter what it is, whether it's a user or what have you, we can kind of get or set some information. So I know I'm almost at time, but I just give me a couple more minutes and we'll kind of finish up quickly here. Similar to this data segregation is this something called a satellite solution. So because, again, the contracts are immutable, we talked about just how you can segregate the data and the logic here. But because changing the contract sometimes requires the deployment of a new contract, how we do this is we're going to outsource functional units that are likely to change into separate so-called satellite contracts and have a core kind of home contract that references these contracts in order to utilize its needed functionality. And so basically, if we have our satellite contract that we think might change, in this case, it's a very simple one that just calculates variables, in this case, 2 times 3. Then we have our base contract that, again, we have our owned keywords as extending owned. And then we can say, using this set variable function that only the owner can specify, we can now here update what the satellite contract is. So if you think certain parts of your business logic will change over time, you specify them here as a separate contract and then just have it do some ownership control that only you can specify, that now your contract is going to be plugged in to this satellite contract. And then in this case, when you're kind of using the satellite contract set variable function, you can just call the calculate variable. If you change this, it'll change the method that it's calling here because you're changing the satellite in the set variable function. In your update satellite address, again, you put in the address of the new satellite. You specify only the owner can do this, and then the satellite updates this way. So almost done here. For contract relay, we have our contract participants must be referred again to the latest contract version as a kind of the last piece of this. And so you have some kind of proxy contract that's going to relay requests to the most recent version, whether it's the most recent auction or what have you. Again, this approach forwards the function calls, including their arguments, but cannot go backwards necessarily and return all the results. Another drawback of this is that the data storage layout, again, needs to be consistent with the newer contract versions, otherwise data can be corrupted. And so, Another system we have here is a contract register. In this case, the participants, again, I'll refer to the latest contract version. And instead of just relaying the arguments like this last contract that we just looked at, really, it doesn't have any arguments, but it could just relay arguments to the latest contract that keeps the same method names. Instead, you can have a register that instead of just relaying the arguments, you instead are going to always, just similar to the ENS, you just simply point to the next contract and have it call the contract, interact with the contract there. And here is the code. You can read this a little bit in more detail. I just want to get back to the last methods of security. Some of the security attacks that we might be wanting to prevent are this mutual exclusion attack that actually has caused major issues in the past. If you look up, we'll kind of discuss later. When one contract calls another contract, as we just discussed in this relay example, it hands over control to another contract. Then the called contract can then in turn re-enter the original contract that it was just called in and try to manipulate its state or hijack the control flow through malicious code. And so, again, I'm not going to unfortunately go through this in detail. I'll try to maybe give a recording offline to follow up this lecture so you can kind of walk through some examples of this insecure contract because it's pretty interesting. But in general, our solution here is to utilize a mutual exclusion modifier to hinder an external call from re-entering its caller function. And so basically what we do is we create this locked variable, and once we're passing on control to another contract, we're locking the current contract that we're in the time being, such that we're not allowing it to we're not allowing the contract to be interacted with until whatever call we made finally resolves, and we can continue on with the logic of the current contract that we're in. For emergency stop, again, since the contract is deployed and executed autonomously, there's no option to automatically halt it in case of a bug or security issue. So you can incorporate a major emergency stop into the contract by triggering a third party to disable some sensitive functions. And so simply, you do this by having a Boolean that says if a contract is stopped or not. You halt it. You have a modifier that says halt in case of emergency that triggers if it's not stopped. And you have here a method that only the owner can trigger that will toggle this contract stopped on or off. And in this case, if you have deposits or withdrawals that are being taken place by different people interacting with this code, you can have the owner ping it and say, okay, turn it off momentarily. There's something we need to debug. Similar to this, you can have a speed bump. Let's see, I think actually, so we're almost done, but I don't want to keep you guys. So just in terms of politeness, I will quickly summarize each of these, go through them, and then I'll have a more in-depth kind of addendum to this lecture recorded that you guys can go through. So if you need to go, feel free, but I'll just give a quick recap and then a more in-depth one later. Emergency stop, since a deployed contract is executed autonomously on this network, and there's no option to halt its execution. What we do is we create a trigger. Oh, we just talked about this one. For the speed bump, what we do is we slow down sensitive tasks by having some basic a timeout if a lot of people are calling something at a certain amount of time. And so we slow down sensitive tasks on purpose. So if malicious actions are occurring, the damage is restricted by just slowing down this functionality. In this case, we can have a waiting time built into it that will allow us to see if there's any malicious activity taking place. We can rate limit things similarly by kind of having a certain limits to when things can be done, simply by saying if something is enabled at a certain time, we can have something, in this case, be enabled every 1 minute by updating the amount of, by just storing some information here that says how much a certain function should have uptime versus downtime. In terms of balance limit, we can limit the amount of money that's withdrawn from a transaction by if there's anybody who hacked it and who might be stealing all the money, we can potentially create a limit here that will make sure that the damage, the maximal damage is mitigated by putting some maximal amount of funds that can be, let's say, withdrawn at any given time. And in this case, we simply specify our integer value of how much can be extracted, let's say. And then we have our modifier that the balance needs to be less than a certain limit. And then when we're, let's say in this case, depositing money, we'll limit the amount of money that can go into it by saying it should be less than a certain amount or greater than a certain amount previously. So thank you all for bearing with me. I apologize for going over time. I will go into more detail in some of these latter examples. If there's any questions, please feel free to come. Again, Lab 2 is due tomorrow. I'll answer any of the questions you put on Canvas also after the class. Thank you all for your time, and I hope to see you soon. I think it should be set up in the system so that if you specify that you're part of a group, it will audit, like if one person from the group submits, then everybody will. Yeah, so I think in the system is set up right now that it allows you to specify which group you're in for this next round. I can double check, but you don't see that. Okay, in that case, I'll make an announcement, or I'll enable it. In the meantime, you can submit your own stuff on this.
In terms of like content, in regards to like the collecting submission, like in the group ways, we kind of have like groups yeah, then how are we?
How big is it?
Yeah. But then, like, how do you consider the people that are in your group? Or do we like write it in the code, comment on in the code, like the
for this one? Everyone will get the same. Yeah. If you have like interpersonal problems, then you have to separately. But like,
our future project is bigger, right?
Future projects are bigger, and people will get different grades.
Yeah, but
so for this, it should have been capped at 3 people, so 6 people working together is too much.
No. We work separately.
Right.
Yeah. But like.
Yeah. That's one way to do it. In general, I will kind of grade you all.
Because some of my friends like never submit, but I left it in like the comments their full names.
Yeah.
Yeah, that works, right?
That works.
Okay. But do we have to like join a group in the future for like the future projects?
So I will double check
this. How big is the size of the future project?
The future project size would be around 6 people.
Yeah. Okay.
And I guess there was some confusion about this, so I will double check it. Usually what happens is that Canvas allows you to specify what you're in.
Yeah.
But you might not check that until you're done, so maybe that's why the confusion happened.
I think you can join a group like under the info tag.
Yeah.
But then it's not there.
Yeah. So I think that's a confusion.
Yeah.
So I'll make an announcement about that for class.
Yeah. Okay. That'd be nice. Thank you.
The thing where I put like 0.5 is my portion, but then it gave an error, so we put 0.5. Why is it so that it's an error?
Because it just wants you to use the most updated version.
But some of my friends use 0.5, and we both have the same link, so it's like 1.5.
That's something I'll have to double check.
Okay, thank you.
I think I know why for you.
Oh, we have actually a potential answer here.
It's like the basics, right? They allow you to select the version of the technology. So if you use 0.5,
yeah.
because the compiler uses the data.
So the person who did 0.5 just auto change it.
I think they went to change the version. That's what I did.
So there's no effect, it's just the same.
It's just the same. It's just which version you use.
Just how you.
Clarify what you mean by this slide.